I wanted to kind of just start off is to kind of lay a little bit of a foundation and ask the question, does God actually call people into scientific careers? And my answer to that's going to be yes. But I just wanted to kind of start off. I'm going to ask you a lot of questions. So if whether you're going to talk or not, I'm going to make you talk at some level. But my question to start off is, does anybody know what this is? Or rather, what would you guess this is? A scatter plot. Okay, we got one vote there. What else?
Bunch of locations on a map you can't see.
Bunch of locations on a map you can't see.
Constellation.
Constellation, all right. Take one more. Come on, somebody's got to get one more.
Stars.
Oh, it's stars on a constellation, yeah. So you may not get this, but this to me is a reminder that God has called me to be a scientist. You never would have guessed that, really? It just seems so clear to me. So let me give a little bit of the background for that. So two of my earliest memories. One was my dad is a PhD chemist, taught at the Missouri Western State College / University for a number of years. But when I was 3 years old, we just moved to St. Joseph, Missouri. My older brother was involved with a group, and he and one of his colleagues had set up a chemistry demonstration down in our basement. And he would dip a ball in liquid nitrogen and throw it on the wall, and it'd shatter, and he'd put stuff together, and it'd make weird noises, cool smells, odd sounds, all sorts of stuff. And I just remember from my earliest age just being fascinated with the way things worked. If my dad were to do that demonstration right now, I would go watch it again just because it's that cool. And you get to understand why do things work the way they do. But probably within about 8 or 9 months after that, one other early memory I have, I was three then, I think 3 or 3 to 4 by this time, was watching my parents be baptized in the 102 River just outside St. Joseph, Missouri, where I grew up. And so here I've got my interest in science and Christianity as an integral part of how I've lived. And so this idea that science and faith are in conflict kind of intuitively just didn't ever resonate with me because I've been interested in science. My parents are teaching me about Christianity. I'm learning, knowing what's going on there. And so, I personally became a Christian in the 5th grade. I told you my story about how I was talking with Hugh there in college and thinking, oh, wow, this is how this all works. Well, fast forward to my first year of graduate school. And I've gone through my first year of graduate school. And when you get done with your first year of graduate school, at least at where I was, they have this cool thing called a qualifying exam. And this is a great test because basically if you pass the test, they allow you to go on and work towards a PhD. And if you don't pass the test, they basically say, thanks for playing, go do something else. And my trajectory all along had been, I'm going to go to graduate school and I'm going to get a PhD. That was where I was going to go. Because in talking with Hugh, there was this recognition that if you're going to talk to scientists, that's the credential, or kind of a minimum credential you need to be able to do that. And so here I am, I'm going through my summer after my freshman year of graduate school, getting ready for this qualifying exam, and just really wrestling with a lot of doubt. I mean, I'm convinced here that God's called me to do this, but I'm like, I don't know. There was another ministry I talked in where, okay, so you don't actually need to have a PhD, and so I'm thinking about that. And as I'm studying, as good as I am at tests, I'm just dreading this test. And so at one time, I got down as I was going through my quiet times, and I'm just saying, okay, God, I'm not ready for this. I don't think I'm going to pass this. I don't know what you want me to do here. But if you want me to continue on this path, this is what I pray. I pray that you would help me to pass this test. But to keep me from getting a big head about things, make sure that I'm the last person who does. Now, on these tests, they always come in and they give you these nice discussions, and the reality of it is about half the people pass every year. So I had a relatively large graduate class, and there were 40 people taking the test that year. So August, you take it on 2 days. You come in 8 o'clock till noon. You take a classical exam where you're dealing with classical physics. They give you a day off, and then you come back and take another 4-hour exam on modern physics, and then you don't hear anything about it for a long time. And so here I am. I don't remember what day of the week, probably Wednesday afternoon. I'm teaching a lab. It's after 5 o'clock. The door's shut. I'm sitting there. We're going through this 3-hour lab, and I get a knock on the door. I go over and open the door, and here's my major professor. My immediate thought is, oh, what did I do wrong? Because why is he coming down to my lab? And so he goes, hey, Jeff, we got the results back. Do you want to hear? I'm like, well, that's kind of important, whether it's good, bad, or other. So he brings me out into the hallway, and he goes, we got the test back. This is what the scatter plot looks like. So you're right, it is a scatter plot. And he goes, what you've got on this here is you've got a classical component on one axis, and they rank your score there, and you got a modern component on the other axis there, and all 40 people were grouped into this cluster. And he goes, you'll notice there's kind of this nice dividing line there that separates the passes from the not passes. That's me. So I'm like, all right, this is what God wants. Now, one of the things that I would encourage you to begin thinking about is you will inevitably, as you go through your college career, you're going to encounter challenges, especially if you go into some sort of graduate degree. I know Mike will talk about that. There's just a lot of challenges, and being clear of what God wants is really important. This was one of those anchor points that as I continued to go through graduate school, wrestle with, can I get this project done? The data didn't work out right. This thing I'd been working on, at the end of the day, it's like, no, God's doing this. God's working at this. He wants me to keep working. And so as I did, I continued working. And the reason why I'm pretty convinced, actually not pretty convinced, I'm really convinced that God does call people into scientific careers, and he's probably called many of you into that, is because science has this great opportunity to tell us how the world works, to inform us about who God is, and allow us to do the work that he's called us to do. And as I was thinking about that, there's kind of 3 things that I see that flows out of doing science that helps us do that. And the first is that it actually just tells us a lot about who God is. As I was actually just going back and reading Psalm 19 this morning, and it says, the heavens declare the glory of God. The sky above proclaims his handiwork. And so I just wanted to kind of take a survey of some of the ways that as we study science, we learn about who God is and what he's done, and just get a bigger picture of this God that we serve. So, like I said, I'm going to ask you a lot of questions. What is this? Now, looks like 2 gears. Okay. Cell wall, maybe? Where do you think you would find this? In front of a jacket? Oh, kind of like a zipper? Okay.
On the microscopic level?
You think so? Where?
Body somewhere?
Inside the body somewhere. Because you're right, it is a couple of gears, and this is what it's gears to. You notice it's about 20 micrometers. So this is kind of width of a human hair type stuff. But this bug on in its, what do you call when you're young? There's a certain term, I hate that, juvenile bug, there we go. You got a juvenile bug. What this bug does is on its rear legs, it actually has this gear so that when it flexes the muscle, it jumps straight forward. But I just find this interesting as you look at that, and it's like, we make gears like this. And what I find is, as I've read through the scientific literature and done various things, is that as we look at creation, we actually find that humanity is imitating nature. And I find that interesting because when we talk about gears and when we talk about designing this to do that, and then we go out and we look and see that same sort of thing in creation, or where we look in creation and we say, oh, wow, that's elegant, and then we actually use that to build a better mousetrap, that to me says that there's a remarkable design and a purpose and a fine-tuning behind creation. And that tells us something about the Creator. Anybody know what this is? I'd be a little impressed if you get this one. Take some guesses. What's that?
The retina?
The retina? Okay, I'm impressed.
The other thing was layer, something,
I have no idea what a peptidoglycan layer is, so I can't tell whether that one's right or wrong. So it's actually not the retina, because the retina is way back here at the back. Sorry, the laser pointer doesn't show up on there. But one of those things that you will hear, or that often goes out there is, wow, the eye is really poorly designed, because the light-sensitive part of the eye is at the back of it, and there's all this junk in front of it. And if you want the light-sensitive part to work, why would you put all the place where it's sensitive, why would you put all the junk in the front of it? That's not a good design for an eye. Not a good design for an optical system. Well, one of the things they found as they've investigated further is that one aspect of that light-sensitive layer is that it generates a lot of heat. And so if you put that down in the middle, you've got to figure out a way to get all of that heat out, which is kind of challenging to do. But if you put it out at the back, you can put all the cooling just right on the surface of it there. But you still have this problem of all the wiring and the circuitry to run the eye is in front of it. So what's going on there? Well, what they found is that actually, when you look up kind of at the front here, all of that stuff, it actually has light guides that funnels, or the materials that work like light guides that funnel the light to the back, so that even though there's all this stuff, you actually get a good image out of it. It's actually a pretty remarkable design. That we do. We just see amazing designs as we look at what we find in creation. But you know what this one is? A tree.
The reflection.
Tree. How'd you get a tree out of that? I'm just curious. It looks like the top of a tree. All right. What would you say? Aurora Borealis. That's actually what it is. And I cannot claim to have actually taken this picture. But there was a fellow who I interacted with who's kind of challenging some of my positions once. He's actually kind of he goes out in search of these. And he's got some videos on where this is actually kind of a mundane picture of what it looks like. It's actually, the aurora is just kind of dancing around, and it's purples and greens and whites. And I mean, it's just really quite beautiful. It's just awe-inspiring, the imagery you see. And as I find, as we look out through creation, as we take pictures of distant galaxies and of nebulae and gas clouds and everything, and even when you get in and look at the cellular structure, just throughout creation, there is just some incredible imagery out there that, while we talk a lot about the fine-tuning and the intricacy of creation, there's a part of creation that just says, wow, the God that made all this is not just concerned with the engineering of it, but he's concerned with the beauty and the artistry of it as well. And then this one, I would guess a fair number of you know what this is. What is this? The CMB, which stands for? Cosmic Microwave Background Radiation. This is actually a picture of the universe when it was 400,000 years old. And as we study this picture of the universe, we get information about how much dark matter is in the universe. Does dark energy exist? When did galaxies form? When did stars form? How does it all work together? Just by taking some of these images, we get incredible amounts of knowledge about the universe. I mean, think about that for a second. We live in a universe that is 14 billion years old. We can actually take a picture of what the universe looked like when it was 400,000 years old. I mean, I do have pictures of me when I was 3 years old, but that was because my parents existed when I was 3 years old. As humanity, we don't exist when the universe was 400,000 years old, but yet God has left this picture in there that allows us to understand what's going on in the earliest moments of creation and get information that would be almost impossible to get otherwise. In fact, the light that we're seeing from here has been propagating through space for nearly 14 billion years, and we're just now seeing it today. Seeing it as it looks tells us what's going on 400,000 years after the Big Bang. I just think this is funny. It's just, it's like cosmic emoticons, that's actually, as like we've gone through, it's like emojis were something else now, so that kind of dates me a little bit, but I just thought that picture was pretty funny. So who knows what this is? A fence. Yes, there's a fence. That's not what's interesting about this picture. The grass. Yes, there's grass. That's also not what's interesting about this picture. Everybody from Southern California is at a distinct disadvantage for this, but if you're in the Midwest, you might catch it. The lightning bugs, yes, these little dots down there. It is incredibly hard for a non-photographer to take a good picture of a lightning bug. I spent the better part of an hour trying to figure out how to do it. That's the best one I got, outside of this one, where I got a picture of the lightning bug and my aunt and uncle's dog. Now, lightning bugs are pretty cool. I mean, you could talk about the design of them because basically they have these two chemicals, they come together, they produce light with almost no heat out of it, which is important because if you're a bug flying around, overheating is going to be a bad deal. But you also have this light produced in a liquid medium that has to get transmitted out into a gaseous medium. And anytime you have an interface, you have reflection off of that. And so the transmission of light through that boundary is going to be small. Well, it turns out that as you look at the scaling of how all the scales and the mechanical structure is, it actually enhances the light transmission by about 50%. In fact, we've taken that sort of technology, put it on top of LEDs, and increased the efficiency or the output of the LEDs by 50%. That's all interesting, but the reality of it is they have a light output of about 1. I mean, there's a certain time of the night where if it's in the day, you can't see them because 1, they don't do that, but 2, it's just too bright. If you want to catch them, you've got about a half-hour window where it's bright enough that you can still see the bug as it's flying around, but dark enough that you can see the light. And we would spend a lot of time collecting these things. I actually caught 3 of them, put them into the jar, poke the holes in the jar so you give the illusion of giving the bugs air so they're not dying. And when I was about 12, I had this ingenious idea of let's let these things go in my grandma's house. So I did. Mom wasn't real happy when she found one in the potato salad that night. But we got that one out. But my brother and I, we ended up sleeping off in the back room, and so we got sent off to bed. Never did find the other 2 until we went to bed that night. Because we're sitting there in bed, and boop, boop. So we got the 2 lightning bugs, threw them out. All that to say this, these things are not particularly bright. But imagine now, if you kind of get a sense of how bright they are. And everybody's seen one of those big spotlights, come shop where come here and look at my store type thing. Imagine, if you will, putting one of these lightning bugs right on the rim of one of those humongous spotlights. Those spotlights emit about 1 billion times brighter beam than these lightning bugs. And then if I tell you, hey, build a telescope, build an instrument that can find the light of the lightning bug. Think you can do it? Believe it or not, we're close. But if you want to find planets outside our solar system, that's the problem you have to solve. We're not quite there yet, but we're within about a factor of 10 of doing it. And so we actually just have this remarkable technology that flows out of doing science. And as we do that, we can take this technology and learn cool things about the universe. So everybody knows what this is. Moon, yes. Who knows what this is? It is. Do you know which one?
No.
It is the Hubble Space Telescope. Somebody in there said that. Hubble Space Telescope's about the size of a bus. I think it still is, but at the time, it's by far the most powerful telescope we had. In fact, even when it wasn't working properly, it was still the best telescope we had. Now, if you take the Hubble Space Telescope and point it at the moon, which would be stupid because you can do a bunch of other things with the Hubble that are not that, you'd see a region about that size. So it would actually take 50 times to cover the whole surface of the moon. I was just doing that to give you perspective. So now if you throw the moon away, look out into the deepest recesses of space where there's nothing, this is what you see. A big gray square. Now actually you see this. Now, question for you. How many stars are in this picture? And it's multiple choice. Is it 5? Is it 500? Or is it 5,000? Everybody has to vote. How many say 5? Okay, we got 1. How many say 500? How many say 5,000? You're going 500? You're going 500? Okay, how many say 5,000? All right. The answer is 5. Somebody will think, yeah. Here's a star. See a little crosshatch there? In fact, one of them's off the edge here. There's another one up there. There's one right there, and there's one right there. And then one's off the bottom because we're doing 16 by 9 instead of 3 by 4. The reality of it is, every other object in that image is a galaxy with millions, billions, and trillions of stars. Now, I think this image is really cool. I actually have half of it, blow it up to 3 feet by 7 feet, and it's hanging on the wall in my office. I just like looking at it. Because when you look at this image, you see just incredible things. I mean, you see, if we take part of it and blow it up, you see you've got galaxies of different, there's one of those stars. You've got greens and reds and blues. You've got galaxies that are nearby, galaxies that are far away. You're seeing galaxies that light has been traveling from these galaxies for 10, 11, 12 billion years. So we're seeing galaxies from the earliest moments of the universe. We're seeing galaxies from later on. It just gives us a wealth of information as to what's going on. Now, what's also cool about this, there are about 10,000 objects in that, 10,000 galaxies in that image. But if we can now go through and count up how many stars are there in those galaxies, how many galaxies are there, we know what size that is on the sky, we can actually tell how many stars there are in the observable universe. And that number comes out to be about 100 billion trillion, 10 to the 23 if you like scientific notation. About the number of atoms in a gram of hydrogen, and roughly similar to the number of grains of sand on the surface of the Earth. I just think that's kind of cool.
Wow.
It is, yes. So, when we look at creation, we just learn a whole lot of stuff about how God's done things, what's out there, and who He is, and some of how He wants to relate to us. But I also find fascinating that as we investigate what's going on out there, we actually develop tools that show how Christianity accurately describes what's going on in the universe and gives us tools to go out and tell others about who God is. I'm thinking of Luke 10:2. The harvest is plentiful, but the laborers are few. Therefore, pray earnestly to the Lord of the harvest to send out laborers into His harvest. We want to be able to go out and tell others about who Christ is. And we need to have tools to do that. And some people aren't going to listen to what the Bible has to say. And so science actually gives us this opportunity to engage them in a way that they might not otherwise listen. One way that plays out. Think of the requirements for humanity. What would you say? I've got 3 that I'm going to talk about. What would you say some of the requirements for humanity are? If you're going to have, what? Got to have an atmosphere. Let's go a little bit more foundational than that even. Got to have oxygen, okay. Water, got to have water. Habitable planet, yeah, you got to have water, you got to have a place for that water, and then there's one other thing if you're going to have life at all, there's one really critical element. Carbon, yes, you got to have carbon. So you got to have diamonds. No, actually, diamonds is just a great way to show carbon. You got to have water, you got to have a place for it all to come together. So let's now ask the question, what has to happen in a universe for all these things to come into being? Well, when you begin to ask that question, you get answers that say it looks like it's designed to be here. I put up a quote from Fred Hoyle. A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as with chemistry and biology. Now, I want to point out here, I'm going to show you 4 quotes. All of them are from people who are not Christian and who are relatively antagonistic towards the Christian faith. So these aren't people saying, hey, this is God doing it. But what there are, these are people who, as they've understood what's going on in creation, how this all works, how we have carbon in the universe, how we have oxygen, how we have water, how we have planets, they're saying, it looks like somebody's making this all happen. It looks like it's all designed. Roger Penrose, I would say the universe has a purpose. It's not there just somehow by chance. Paul Davies, seems as though somebody's fine-tuned nature's numbers to make the universe. The laws of physics seem to be the product of exceedingly ingenious design. Now, as we have studied creation and figured out what does it take to make water, why do we have carbon, why do we have planets, how does it all work together, the idea that the universe looks designed is not a controversial idea. But we only know that because of having studied the universe and figuring out the way it works. One way that plays out, and this one I thought was kind of interesting, is go back into the 1920s. We finally realize, okay, there's 3 large spatial dimensions. There's 1 time dimension. What happens when you change that? You go down here. We're here, kind of right there. 3 spatial dimensions, 1 time dimension. If you make fewer spatial dimensions, so go down to 2 dimensions, we can kind of envision what that might look like. We're on a piece of paper now. Well, so imagine you've got a creature, 2-dimensional creature, that wants to eat, ingest food one place, and expel it somewhere else. 3 dimensions, that works great. But in 2 dimensions, you run into this problem. So you've got your creature there. Food comes in, digests, goes out. In 2 dimensions, you've now cut the creature in half. Now you might say, okay, well, you could have the food come in or go back out. But it turns out it actually illustrates a far more fundamental problem, is that in 2 dimensions, there is not the complexity you need for life. Life requires at least 3 physical dimensions. Or physical life requires at least 3 dimensions. Then you say, well, what happens if we go to more dimensions? Let's go to 4 or 5. Well, it turns out if you go to 4 or 5 dimensions, it turns out that nothing is stable. So in 2 dimensions, you can have a planet orbiting around a star because that works. In 4 dimensions, that no longer works. The planets either fall into the star or fly off into space. And it turns out atoms are not stable. So if you want to have life, given the laws of physics, you need to have 3 spatial dimensions. Now, you go out there and you say, all right, what happens if you change the time dimensions? Well, physics becomes unpredictable. I met a lot of people who say, well, I don't know how to do physics. The fact that it's unpredictable doesn't affect me. But it's actually, again, a more fundamental problem than that. Because all of life requires this feature. Life is here, detect the environment, figure out either what's happened in the past or what's going on in the future. So, amoeba floating around saying, I need food. Not thinking this, but thinks, I need food. It senses an environment, knows that there's signals saying danger's there and food is over here, so it moves. If physics is unpredictable, that can't happen because what's going on now has no relevance to what happened in the past and no relevance to what's going to go on in the future. So physics being unpredictable isn't, I don't know what's going on, it's that life cannot operate if physics is unpredictable. So we see design out in the fabric of space-time. When you look at it in terms of the strengths of the forces, we talk about fundamental forces, and Mike's going to get into this later in the week, but I just kind of wanted to hit one thing, is that we can actually study what happens when you change the strengths of the forces. And it turns out that there's a whole large section where carbon just doesn't exist. And you get only relativistic atoms, where everything's always moving close to the speed of light relative to one another. You don't get life because nothing will clump up there. You could end up with no hydrogen left in the universe. That's also a problem. And it turns out there's this kind of small region just right in that little area there where everything comes together for life to work. So in all the different ways we could envision the laws of physics put together, only this teeny tiny region allows all of the things necessary for carbon and oxygen and hydrogen and planets to exist. When we look at how our Earth formed, one of the last events that characterized the formation of Earth was that Earth was hit by something about the size of Mars. And when that object hit, created a big collision, but it did so in just a way that after time, Earth ended up with a large moon. Now that large moon plays a very critical role for Earth being habitable. Because if you don't have a large moon, Earth spinning around on its axis is just going to kind of flip around every now and again. In fact, we see that on Mars. Well, that happening is going to dramatically change the conditions on the planet, probably going to get rid of all the water and all the life's going to end up dying. It also adds elements to Earth, which allows plate tectonics to operate for a long period of time. It actually sped up the rotation of Earth so that over time it could slow down so that we can enjoy 24-hour days. So this moon event, or the moon is critical for how Earth is habitable. But this event that created the moon is very finely tuned. It's not just your run-of-the-mill random ordinary collision. It's actually a pretty special collision. Even in the way the solar system forms. So To get solar system formation, you start out with this big cloud, things clump together, you form large objects, eventually you get planets out of that, but there's a lot of junk left over in the solar system. That junk ends up colliding with Earth, causes dinosaurs to go extinct. Big, major collisions. I mean, things that are a mile size are going to do a huge amount of damage. Well, back in 1994, when I was in graduate school, we got to witness a comet that hit Jupiter. And as this comet comes in and hits Jupiter, you kind of can't see it here, it doesn't show it, but it actually caused scars on Jupiter that are twice the size of the Earth. I mean, it's just an enormous amount of energy. Any one of those fragments hitting the surface of the Earth would emit or release more energy than the simultaneous detonation of the entire nuclear arsenal of the world. And the nuclear arsenal wouldn't even be close to how much energy is being detonated here. So this has just caused huge amount of things. But when we look at how that played out in our solar system, if that were to happen today, it would be catastrophic to life because we got a lot of complex life. But there was an event that happened early in the history of the solar system that basically cleaned all of that out and reduced the collisions by a factor of about 1,000. So whereas now we have dinosaur impacting events or dinosaur extinction events every 100 million years, had it not happened in the early solar system, that would happen about every 100,000 years instead of 100 million years. Well, 100,000 years is the time scale of humanity. Kind of have to ask the question, if something like that's happening where you're extincting a major part of the surface every 100,000 years, are you going to have a planet that's particularly conducive to life? You know, and we see evidence of this past event when we look out and look at Mercury and we look at the moon. You know, and even looking at the size of the Earth, we tend to think, all right, planets can be whatever size. I actually remember doing a study or doing a problem in one of my astronomy classes when I was an undergraduate, which you calculate the surface gravity of Earth. And it turns out that the surface gravity of Earth is just large enough that anything with a molecular weight of 18 or larger stays on the Earth. You think of any important thing with a molecular weight of 18? What important thing has a molecular weight of 18? We got to have some chemist in here, don't we? Water, yes. Oxygen 16, hydrogen makes 18. It's just enough to hold on to water, but it's not strong enough to hold on to anything with a molecular weight of 17 for very long, which is ammonia and methane and other things lighter than that. So those things will float off to space, whereas the water will stick around for a long time. But it turns out that even when you're considering plate tectonics, as we've studied what causes plate tectonics to occur, for plate tectonics, you got to have rigid plates that can float around on top of a more malleable surface. Well, it turns out there's a particular attribute of the interior of the Earth where about 100 miles to 200 miles deep, there's the solubility of water in rocks goes way down, and so it makes it a more fluid region, and it actually sucks water out of the stuff above, so it makes more rigid plates and a more malleable surface, and that's what allows this plate tectonics to happen, which is critical for water being here on the surface of the Earth. And so if that were any deeper, the plates would be too big and they wouldn't move around. If that were any shallower, the plate tectonic activity would be far too much. And so again, we see evidence in design even in the size of the Earth. And the point of all this, we kind of scooted over a lot of that, is that we see evidence that this is a place that has been fashioned for us to live. And even when we look down into the cell, again, the idea that things look designed is not controversial. Francis Crick, the co-discoverer of the double helix nature of DNA, was awarded the Nobel Prize for that. He goes, biologists must constantly keep in mind that what they see was not designed, but rather evolved. To me, I mean, whether evolution's right or not, the idea that it looks designed is not a controversial idea. One way that plays out that I'll just talk about, I am not a biologist, I know very little about biology, but I do a lot of computer programming. And when we look at the DNA of that's the backbone of all life, it is a code. It's a computer code, if you will. And it works in one particular fashion of it. There are certain parts that code for proteins, or for amino acids which make up proteins. And there are 4 letters to the code. There's A, T, C, and G, U, C, A, and G. And they come together in groups of 3. And the group of 3 will specify a particular amino acid. And so you can see there, if you go up and you look at phenylalanine, that can be UUU or UUC. And for leucine, there's 6 different options there. What you'll notice, if you put 4 letters and have 3 options, that makes 64 possibilities. 4 times 4 times 4. There are 20 different amino acids, so that means there's some duplication that goes on there. What scientists have now been able to do is look at that and say, all right, that provides an ability to cope with errors, because when something so one of the U's changes to an A, does that actually change what the program outputs, if you will? And they can do a study of how well does the genetic code minimize errors? And it turns out that you can do a study of that and you can put it on a normal distribution and just kind of give you a sense of what that looks like, where those numbers mean. If you do this with IQ, not making any statement on the validity of IQ, but it does kind of provide a measure of how outside the norm are certain things. So if you put 100, that's the middle, half above, half below. If you go out to 130, those are pretty bright people once you get out there. There's not a lot of people above that. You can kind of see where in the curve you're getting there. You go out to 150, that's what used to be Mensa Genius IQ, what you had to have to get into that. You go out to 170, these are people like Einstein and Picasso and people, that's the class of people you're talking about there. When you look at how well does the genetic code do in minimizing errors, just in this one sense, it's way out there. The genetic code is literally 1 in a million in its ability to minimize errors and to do what it's supposed to in a harsh environment. This is one reason why we look and say, wow, things look designed. And this just leads to this very natural conclusion. It's where we see evidence of design, it's natural to conclude that a designer exists and that a designer created this universe to support humanity. So we can learn about the Creator, we can develop tools to share the gospel with others, and we can just take care of people well. One of the commands, for I was hungry and you gave me food, I was thirsty, you gave me drink, I was a stranger, you welcomed me, I was naked, you clothed me, I was sick, you visited me, I was in prison, you came to me. Jesus was saying, hey, you need to take care of my people. You need to take care of people. And by using science, we can do that. Most everybody here has one of these. This would not exist had we not understood how semiconductors work and how electricity works. There's a whole history of science that allows that to happen, that gives us tools to help people who otherwise we wouldn't be able to. We can communicate, we can spread information, we can do good things with it. Anybody know what this is? Chemical structure, so the red balls, gray balls, and white balls mean different things, but anybody have a sense of what this is? You guys may not, because you probably don't need it a lot. Everybody back here has probably used this at some point in time. This is naproxen, otherwise known as Aleve. When you spent too much time bending over in the garden or played one too many basketball games, this is what you take to reduce the inflammation and get rid of the pain. But we can design and develop medicines and drugs that help people do things that they wouldn't otherwise been able to do. We can engineer things that allow people to have mobility. I had a neat opportunity a few years back to take a mission trip down to Guatemala. And one of the things they did was they just took wheelchairs and they refashioned them and they gave them to people, because now people who are otherwise confined to immobility could get around and actually could do things. So we can do good. We can make vaccines that mitigate diseases. By and large, you guys just don't even have to worry about a lot of diseases that I only remember hearing about from my parents, because we've been able to take care of them. These are diseases that would literally kill millions of people that we just don't even have to worry about, because we can give vaccines to people. And, again, we take for granted that we have water everywhere, that we can get good, clean water. When I was down in Guatemala, they were telling us, don't drink the water, because if you drink the water, you end up getting sick. Well, this is the water supply for various people. And now we can go in and build wells and get them clean water. So we can actually do what Jesus is telling us to do, is to go out and serve others, to take care of others, and give them the resources they need. So, does God call us to be scientists? Absolutely, He calls us to be scientists. Is science a good thing to do? Absolutely, because it helps us understand who the Creator is. It helps us articulate and spread His message, and it helps us take care of the people He's given us to take care of. And so I don't know what God has in store for you as you guys pursue your scientific careers. But I would encourage you to start thinking about is God calling me to do this? What is He calling me to do? How can I do what God's been asking me to do? And then be all in about pursuing that. Because I am convinced of this, that what God calls you to do, He gives you the resources to do. And so in the challenges you're going to face, the struggles you're going to have, and the joys you get, God's going to be there taking care of all that.